Hello and welcome to CS 4010. In this tutorial, we are going to study the second half of the tutorial about the vibration of structure. So in last step, we have started how to input the matrices. And in this tutorial, we are going to do the simulation. So first of all, I need to set a parameter for my simulation. So first of all, I need my final time, for example, 0.2 seconds. So this will be a like check. So it's my final time of simulation. And my DT, the time step, I take it here about 10 milliseconds. So this will be my time step. And now I need to have some initial load for the structure to vibrate. It can be cyclic load or can be a shock from earthquake. So in here, I take my U initial equal to 0.1 times by 1 of n by 1. So this way, my initial displacement will be 10 centimeters for each floor. Yep. And because the building cannot move by itself, so I set my V initial equal to 0. So this is my initial velocity of the floor. It is 0. And I get my x, the real x I'm going to use for plot later, equal to x at equilibrium plus U, which is a displacement. So this is my initial coordinates. Yep. And I set the x limit and y limit for the plotting later. So I have my x lim equal to from minus 1.1 times by the max of ABS of x to about 1.1 of the max of the ABS of x. So this way, I will have the absolute of the x coordinate first, and then get the max of them, and then go from minus 1.1 to 1.1. This way, I will have a little space for the vibrations. Okay, so this one will be my x range for plotting later. And my y lim similarly equal to minus 1.1 times by max of absolute value of y to 1.1 of max of absolute value of y. Yep. So this will be my y range. Now I need to set up the timer as I used to do for my simulation. So my timer at the beginning equal to 0. Set timer. And I start calculations. You know, to do the matrix form, you need to solve the main equations. And this equation can be use some approximation like you have seen over here for the finite difference method, or in general for all other numerical method as well. And at the end, you need to calculate the future variable based on the current variable and the past variable. So you need two of them. This one will be my K, this is my A1, and this is my A2 for the parameters. Now, I set this one up, so I need to calculate the force. F equal to F of 1 times by the sine function of the angular velocity should be F of 2 times by time plus F of 3 minus stiffness times by the U before, where U before is the previous displacement. So this one will be my F, my force. It's external force. plus the initial elastic force. Yep. And the U before, I get it from the U. So I set my U before equal to U. So this will be my initial displacement. And now I need to calculate the U after the first one. And then I can loop it over and over again. So I have U after equal to U before time by V time by dt, which is actually 0 because my V equal to 0, minus 1/2 of F over the diagonal vector of mass. So this vector will contains only the mass, not the 0 elements, and time by dt square. So this is my first calculated position with the assumption that the acceleration doesn't change in that small interval. Okay. Now I need my parameter, my k equal to invert of 1 over 2 over dt time by damping plus 1 over dt square time by mass. So I set parameters for solution. Yep. And my A1 equal to minus stiffness plus 2 over dt square time by mass. And my A2 equal to 1 over 2 over dt time by damping minus 1 over dt square time by mass. So this is all the parameters I need. So now I just try to make a while loop. In this while loop, I'm going to loop over and over again because I only have two positions, the U after and the U before. So this while loop, I must have this one for condition the time is smaller than the final time. Now I can plot it. So the first of all, I need to get my U equal to my U after. So I move to the next step. I just update the displacement. And then I get my x equal to small x plus U. So I update coordinate here. And I get my time equal to time plus dt. So I just update the time. And now I can just plot it. So I need to use a function named plot structure. I will explain it later. Just type it first. Structure of x and y and stiffness where it's not 0. Time x limit and y limit. I just change this one a small bit so it will not be confused with the MATLAB default keyword. So it will be my x limit and y limit. Okay, and now this function I try to plot the calculated position or displacement position. And after that, I pause for a small time step as I used to do. It can be pause to see the movement. And now after all, I need to calculate the next step. So I have my U after equal to K time by A1 time by U plus A2 time by U before and plus the external force. So it should be F1 times by sine function of F2, that's the angular velocity, plus the phase delay time by time first, and plus the phase delay, which is F3. Yeah, so double check. I need this one should be comma, and I think I need the last one to close the own bracket. So this I calculate the next displacement, and I update my U before equal to U. So in here I update the previous displacement. Yep, and that is for me. Now I need to do this plot structure function because this is not by default by MATLAB. I need to plot it out, so I need to create one. So in here I will make a new section about my plotting function, and I create a function in MATLAB. So I call it the same name like before. It should be plot structure, and I need to require is y connections time x limit and y limit. Okay. In the first step, I need to clear the figure because I don't want the old position in the new graph. So clear the figure. And then I hold on because I'm going to draw a lot of things on this graph. Keep data. Now I'm going to set the x limit and the y limit for the graph. Yep. So in here I focus on the given range. Yeah. Now I get the range of my connection. So I have n equal to size of connection. So this way I can have the n could be the first index and the second index. I don't care about this. I just put a symbol over here. I get number of masses. You know, when you move to a new function, you don't keep all of the variable in the old functions. MATLAB going to copy only the indicated variables into the new function. So therefore, if you don't have it, you have to call it again. Now, when I know my number of masses, I just loop over everything. So for I equal to 1 to n minus 1, and for j equal to I plus 1 to n. So this way I loop over possible connections. So if the connection ij is not equal to 0, the spring has some stiffness. So if there is connection, spring must have a stiffness. Yep. And I try to plot it. I just plot x and y. So plot from the value of x is going to be from xi to xj. This will be my x, and the value of y should be from yi to yj. And the line style, for example, I had is blue, and I have my line width is 2, for example. So I just plot the connection. And that is for the loop. Now I want to plot the mass as well, so I use scatter x and y. So I will plot all of the mass. Now I set the title will be timestamp. So time equal to, I need the time, and certainly the unit would be second. Yep. So in here, I just reset timestamp and I hold up. Actually, I don't need to, but I can hold up because I don't want to mess up with the clear figure command later. Okay, so that is it. Just try to run this code to see if there is any mistake or typos I made on the way. Now just click on run. Okay, I don't see any mistake yet, so I hope it's fine. I try to solve this problem, so my degree of freedom should be 5. Mass of element 1 should be 6 m, and m is 10 ton, so should be 60 ton. My x should be 0, and my y is 1.5 up 2.8. So 1.5 up 2.8 is 4.2. My f is 0.
Now my mass of N2, I have this one is 5 ton. And my x input is minus 10, for example. My y input is 2.7 times by 2.8. Could be. And mass of element 3 should be 10 ton. And my input x is 0, my input y is 7.0. My mass of element 4 should be 5 ton. And input x should be 10, input y 7.56. Now my mass of element 5, which should be 5 ton. And x is 0, y should be 3.7 times by 2.8. So it should be 10.36. And I don't have any f.
Now I need some stiffness for the ground element 1. So it will be this one. I have calculated it here. Should be 323.9 power 6. Damping stiffness. My damping stiffness must be 2.4 power 6. For element 2, I don't have anything here, so should be 0, 0, 0, 0. Now stiffness between 1 and 2 should be K2, 0.63 E6. And my damping stiffness is right here, 0.8.
My stiffness of the connection between 1 and 3 should be K3, 128.8 E6. And damping stiffness 0.8 E6. 1.4 should be 31.63 E6. And my damping stiffness should be 0.8 E6. 1 and 5 is 0. 2 and 3 is 0. 2 and 4 is 0. 2 and 5 is 0. 3 and 4 is 0. 3 and 5 should be K5. Should be 54.66 E6. And my damping stiffness should be 0.8
E6. Okay. Now I got some problem over here. Error using inline structure. Okay, I forgot this one should be dot over here. And I think that is because I try to time element by element. Now, because I don't want to re-input my structure, so I mark all of this one and try to get this one to comment out and try to run it again. Yep. Now something wrong again. So in line 61, in here I need add one dot. Sorry for this. Okay, save. You can see here is my initial one. So this can be my ground level connect to the M1, M2, M3. So it looks like 3. Try to run it again. Yep, you can see the vibration. I try to do it again for you to see the vibrations. But it's going to be very small for us to observe. So now I'm trying to plot out the displacement. So to do that, I need to add up something to store the displacement. So I have my t equal to 0 first. And here, after time, I have my t equal to t and time. So I add time. Yep. And I set my s length of t equal to u. So I try to store u into the variable s. Now at the end, before I do it again, I try to make a new figure and try to hold on. For I equal to 1 to n, I try to do for all of the masses. I try to plot t and s of I. Yeah. So this way I will try to plot the displacement of any mass from 1 to n. Try to see if it works. Now run this one again. Yep. And here you can see is the displacement. It's all come from about 0.1. I set the displacement to 0.1. It all go down and go up and back again. So this is the natural frequency of the structure. Based on this, you can see the vibration. Thank you very much for your time, and I hope you enjoy the tutorial.